the arterial and venous circulation for the brain, and then we're also going to talk about the stroke versus head injury, just really a superficial description of the two. So, of course, you know that the brain is the most important organ in the body, right? Because without a brain, who cares if we have a heart? So, right? So 18% of our blood volume goes to the brain, and it's only 2% of our mass, so obviously it is the most important thing. It uses 20% of our absorbed oxygen and 17% of our cardiac output, so clearly it's very, very important. And the other big thing is that the brain does not store oxygen, so it is aerobic, so we need to have constant blood flow to the brain. So any obstruction of blood flow to the brain is going to cause neuronal damage, and certainly some areas of the brain are much more susceptible to ischemia and hypoxia than others. And so when we get into some of the strokes, we'll talk about that. And then obviously stroke is the leading cause of disability in the U.S. So if you think you're not a neuro person and you're going all outpatient or neuro or outpatient ortho, I guarantee you will see a patient with a stroke if you are a physical therapist. There is no way to avoid this diagnosis. So, and it turns out that everybody who has a knee also has a brain. So if you're treating their knee, it's possible that they could have something wrong with their brain. So you really can't, even if you think, oh, you know, I'm not going to deal with stroke, you are going to deal with stroke. There's just no way around it. Obviously, the first thing when we start talking about the blood flow is the blood-brain barrier. And we talked a little bit about this with the glial cells, but it was really surprisingly when long ago they injected substances into the bloodstream or dyes into the bloodstream, it would stain all of the organs except for the brain. And that's how they discovered there must be something blocking substances from getting into the brain. Now, obviously, some substances easily get into the brain, like alcohol and other psychotropic substances and caffeine. So certainly some can get in through the blood-brain barrier. The other big thing about the blood-brain barrier is that when we have problems like head injuries with increased ICP, the blood-brain barrier's integrity goes down. So substances that shouldn't be getting into the central nervous system do get in. So that's often a problem. The other issue is that if we do drugs into the vascular system, they often can't access the central nervous system. So that's when we might need to do an intrathecal administration. The blood-brain barrier is chemical. We certainly have all the chemical transport sorts of systems there. We're not going to go through them. But it's also physical. And so if you look at a capillary in the rest of the body, you know, obviously not in the important part, it looks like this. But if you look at a capillary in the central nervous system, you're going to see that the endothelial cells around the capillary are much tighter. And these are called the tight junctions between the endothelial cells. So there's an actual physical barrier there. And then the second part of the physical barrier are these guys, which are astrocytic end feet. So these are our glial cells surrounding the capillaries in the central nervous system. So there's our astrocytic end feet. So our blood supply to the brain, we essentially have an anterior circulation to the brain and a posterior circulation to the brain. The anterior circulation is coming through the internal carotids, and the posterior is through the vertebral-basilar system. So the anterior circulation is going to be the frontal lobe, the parietal lobe, the thalamus, the basal ganglia. The vertebral-basilar, for the most part, is going to be the brainstem and the cerebellum, and the posterior lobe, or the occipital lobe. So here it is looking all together in a kind of a 3D view. And so you're going to see, obviously, that the anterior circulation going to the frontal and parietal lobes and part of the temporal lobe is going to mix with the posterior circulation through the vertebral-basilar. And we'll look at that. So we'll start with the anterior circulation. We've got the common carotid coming up the neck, where we were just talking about with the shunts going in the carotid sheath. And then it bifurcates into an internal carotid, which is going to supply the rostral parts of the brain, and an external carotid, which is going to supply the face, the neck, and the meninges. So the meninges are actually supplied by the external carotid artery. So this common carotid bifurcation, just because it's a fork in the road, is often a problem for plaque development. So when they talk about doing an endarterectomy, have you talked about that at all? Mm-hmm. Essentially, they're going to go for an endarterectomy if they do a Doppler and find out that blood flow is decreased. In that carotid bifurcation, they're going to go in through there, and they're basically going to roto-rooter out all the plaque and sew it back up. No big deal. All right, so what's going to happen, now we're looking at an inferior surface of the brain, and these open blood vessels, which we saw when we were looking at the brains in the lab, are the internal carotid arteries have been cut off. So they emerge just lateral to the optic chiasm as they enter into the brain. So what happens, here's our internal carotid, this little open vessel here. Once it enters right by that optic chiasm, it's going to branch into two very large blood vessels right away. One is going to be the anterior cerebral artery, this ACA, and the other is going to be the middle cerebral artery, or the MCA. And what we're also going to see is we're going to see a lot of tiny little collateral branches coming off near this bifurcation. And some of those are listed here. I don't expect you to remember them, but you might, if you recognize any of these other vessels, they're small blood vessels off of that internal carotid bifurcation. And we'll talk about sort of the general picture of them. But you can see a lot of tiny little blood vessels coming off, at least the MCA in this picture. All right, so the ACA. It branches off of the internal carotid, okay, and essentially it's going to come in and it is going to travel superior to the corpus callosum. So it's traveling within the medial longitudinal fissure. So here I have a set mid-sagittal view. You can see the ACA. You can also see it here. Here's our internal carotid coming in. There's the MCA. And here's my ACA. So I've got a right and a left ACA supplying that medial surface of the frontal and parietal lobes. There's also a very small blood vessel connecting the two anterior cerebral arteries, and this is our anterior communicating artery. You'll also see off of the ACA, you'll see some very small blood vessels that are called our striate arteries. And our recurrent artery of Hübner is one of these. And they're going to go and supply the olfactory tract and bulb, and they'll also supply some of the basal ganglia that we'll look at. Essentially, we're supplying this medial surface. So what do you think, just picture-wise, the anterior cerebral artery functionally supplies? As far as if we were to damage the ACA, what kinds of things might you see?
Like the corpus callosum.
Corpus callosum, that's a good one.
Well, I was saying because like then you wouldn't be able to do things like with your
Bilateral coordination kind of things. That would be good. Yes, corpus callosum is supplied by the ACA, so you would have those bilateral issues. Where?
Like medial stripe. You're saying it's
No, but I'll show you that in a minute. The recurrent artery, it's going to go in. The recurrent artery of Hübner is going to go in, and you'll see the striate arteries go into the base vein. I haven't told you that yet. But it does. It goes in.
No,
Okay.
I'm just confused with the wording, but it's,
Oh, okay.
like it says the branches supplies the medial striate artery.
Oh, it doesn't. Oh, it's a separate. I should make it a whole new sentence. Period.
Okay.
How's that sound? Or one, and two. They're not the same. All right, so we've got the corpus callosum. That was a good one. What about here, what are we supplying?
Cingulate gyrus.
The cingulate gyrus, so some limbic stuff, sure. Frontal lobe, so some judgment kind of issues. What about this? What's here? Precentral and postcentral gyrus, specifically. Lower extremity stuff. Remember the lower extremity stick in. So we'll look at ACA strokes, but that's what we see. We see more lower extremity involvement than upper extremity. Now our MCA. Yep. Yeah, and we'll get that. Yep. Yep, and then you end up with all that stuff too. But typically the basal ganglia, if you really got the ACA to get the basal ganglia, you would end up with such a massive stroke, you'd have a lot more going on. So more often you're going to get those striate branches. But the MCA, it comes off of that internal carotid and it dips into the lateral fissure or the sylvian fissure. And so if you open up that sylvian fissure, you open up the temporal and parietal frontal lobes, you'll see this MCA, it's this massive blood vessel. And it's got branches that come up into the frontal lobe, into the parietal lobe, and down into the temporal lobe. So this is just a massive blood vessel. So when someone has an MCA stroke, they might have a stroke down here on this main branch. That's going to be a pretty big problem. Because they're going to have frontal lobe issues, they'll have motor issues, they'll have sensory issues, they'll have some type of something that happens in an area right over here. What's this area? They'll have Broca's aphasia. If it really is this big branch, they're also going to have Wernicke's, so they'll have global aphasia. But if they just got this branch, they might just have Wernicke's. They just got this, they might just have Broca's. So an MCA stroke, depending on how large it is going to have different ramifications. So again, we've got this MCA traveling through the sylvian fissure, and then its branches going onto the lateral surface of the cortex. So it'll get the frontal eye fields, it'll get the precentral gyrus, the postcentral gyrus, it'll get Wernicke's area, Broca's area. It's a lot. So if you actually looked at the cerebrum, this is a lateral view, a medial view, and then a horizontal view. We've got our anterior cerebral artery and our middle cerebral, both coming off of the internal carotid. That's our anterior circulation. The anterior cerebral artery is going to supply the medial surface, mostly of the frontal and parietal lobes, and then just the edge of the lateral surface. The MCA is going to supply the lateral surface of frontal, parietal, and temporal. The PCA, which we'll talk about in the posterior circulation, is going to do some of the temporal and occipital lobes. So mostly occipital, but some of the temporal. Now those little striate arteries. So now we've blown up. We've got our internal carotid here, dividing into the anterior cerebrals and the middle cerebrals. And again, you see all these little vessels branching off, and they can branch off actually of the MCA and the ACA, and they're going to supply the basal ganglia. So remember, the putamen and the globus pallidus together are sometimes called the striatum. So the striate arteries supply the striatum. Now what happens when we damage that is we call it a lacunar infarct, and we'll look at it in a moment. But essentially a lacunae is a hole that's left there from these little tiny blood vessels. So a lacunar infarct is an infarct of the striate arteries. Now, blood pressure is obviously important to supply the brain. If we have too much blood pressure, like hypertension, those little end branches, they basically hemorrhage. So a lot of our hypertensive strokes are of those little small blood vessels. So most often a lacunar infarct or a striatal stroke is a hypertension-related stroke. On the same, or I guess the opposite end, or whatever, same, no, I don't know what it is, whatever you want to call it. When we have hypotension, where do you think blood doesn't end up getting to? The little tiny blood vessels again. So if blood pressure is high, they hemorrhage, and if blood pressure is low, we don't get supply to them. It doesn't get that far. So both hypertension and hypotension end up affecting these end branches. So, that said, we've got our MCA, and as we get farther and farther along, the branches get tiny. And here's our ACA, and as it gets farther and farther along, the branches get tiny. So that the tiny little branches of the MCA and the tiny little branches of the ACA, this is like a good little child story, the tiny little branches come to meet. And they meet in an area called the watershed zone. And that watershed zone is just on the lateral surface of that medial longitudinal fissure, so right here. And so that's where the MCA circulation and the ACA circulation meet. So if we don't have enough blood flow, blood pressure's too low, we can end up with what we call a watershed stroke. And that's a stroke at essentially the junction between the MCA and the ACA territories. So essentially with any problem with blood pressure, it's these little tiny blood vessels that are involved. So we've got a watershed stroke, and we've got lacunar strokes. Then the big cheese, which is the posterior circulation. So the posterior circulation is from the vertebrals, and the vertebrals come together to form the basilar artery. So basically the vertebrals come up through the cervical spine. They have this little loop to get over the foramen magnum, and then it comes up through the brainstem. We're on the brainstem essentially. So before the two vertebrals combine to form the basilar artery, the first branch off there is called the pica. All right. And the pica is the posterior inferior cerebellar artery. So it comes off before the vertebrals form the basilar. And it's going to supply, what area do you think of the cerebellum? The posterior and inferior part of the cerebellum. It's also going to supply, it's in the medulla, so it's going to supply the parts of the medulla. It's going to supply that choroid plexus that makes the CSF in the fourth ventricle. So our pica supplies parts of the cerebellum, the medulla, and the choroid in the fourth ventricle. We already talked about our anterior spinal artery and our posterior spinal artery. So now we've got our vertebrals coming up. Here's our anterior spinal artery that actually came together from the two vertebrals. And then the two vertebrals come together, form the basilar artery, which goes up the middle of the pons. And right after it merges, we've got our ICA, which is our anterior inferior cerebellar artery. So we've got our pica down here, our ICA. Then we go all the way up our pons, and we have our superior cerebellar artery on either side. And then the final bifurcation of the basilar artery is the posterior cerebral artery. So again, we've got our posterior inferior cerebellar, or pica. The two vertebrals come together to form the basilar. We've got our ICA. And then at the rostral end of the pons, we first have our superior cerebellar. And then just after that, our final bifurcation is the posterior cerebral. So our ICA, our anterior inferior cerebellar artery, that's the one that comes off at the caudal end of the pons, right after the basilar forms. It's going to supply, obviously, the other parts of the cerebellum, the inferior cerebellum. It's going to supply the upper medulla and the lower pons, where it is geographically. The superior cerebellar artery is going to supply the superior cerebellum. And then the posterior cerebral artery is going to supply the occipital lobe, parts of the temporal lobe. And the other big thing is going to supply the midbrain and the thalamus. So the circle of Willis. The circle of Willis is the most important anastomosis in the body. Basically, we're talking about a mixing of, or the combining of the posterior and anterior circulations to the brain. Now, in reality, they don't really mix because the pressures keep it that way, but they could mix. The circle of Willis has this, and we'll talk about the traditional circle of Willis, but people's vary. People with long-term problems with blood flow tend to develop a lot of collaterals, so that protects their brain somewhat. Humans, for the most part, don't have a lot of collateral circulation. Rats have a lot of collateral circulation, so to give a rat a stroke, you actually have to occlude at least 3 out of those 4 blood vessels. At least out of the 2 internal carotids and 2 vertebrals, you have to occlude 3 of those to give a rat a stroke. You don't have to do that much to a human. So we don't have quite the protective mechanism. But the circle of Willis, what it's made up of, it's going to basically go around the optic chiasm. We've got the posterior cerebral arteries, which remember is the terminal bifurcation of the basilar artery. Then we've got the posterior communicating arteries. And the posterior communicating arteries, these are really the arteries that are connecting the anterior to the posterior circulation, because they are going to connect to the anterior cerebral artery. And then the 2 anterior cerebral arteries are connected by the anterior communicating. So our circle of Willis is the posterior cerebral, posterior communicating, anterior cerebral, and anterior communicating. So here's our circle of Willis without the rest of the brain. Again, theoretically, if the posterior circulation or the anterior circulation was blocked, the other could supply, but that doesn't really happen. The other big problem with the circle of Willis is that because there's so much branching here, it tends to be an area for weak blood vessels. It tends to be an area where aneurysms develop. So this is just depicting the various aneurysms that are associated with the circle of Willis. And here are some aneurysms on an autopsy. Any questions on the posterior circulation? Through the venous system, and then we'll stop. We'll do stroke next time. So the venous system is really pretty straightforward, a lot simpler than the arterial system. Essentially, what we have is we have a deep cerebral venous system where we have deep cerebral veins, and then the whole purpose of this venous system is to get out to the dura. So it goes from our deep cerebral veins to our superficial cerebral veins, and it's going to get into our sinus system, and our sinus system is in our dura. So again, it goes from the deep cerebral veins to the superficial. Once it gets to superficial, we're going to be in the dura, in our dural sinuses, which will drain it eventually to the internal jugular. So if you, in lab, you looked at the dura, you probably saw some of the sinuses and you saw blood in them, and that's the venous sinuses. They're huge. So what we have, the biggest sinus we have is the superior sagittal sinus, which structures were located there? The arachnoid granulations, so that's where the CSF is draining into. So we have the superior sagittal sinus, which is just at the superior aspect of the medial longitudinal fissure. It's huge again. We've got our straight sinus, which is basically going to drain between the cerebellum and the occipital lobe. So that's going to be, here's our superior sagittal sinus, here's our straight sinus. And they're going to come together at the posterior aspect of the cerebellum, this posterior superior aspect of the cerebellum, and that's called our confluence of sinuses. So just like we have Confluence, Pennsylvania, where all the rivers meet, we have the confluence of sinuses. So it's going to go from the superior sagittal and the straight to that confluence of sinuses. From, oh, there's my blood flow. See? We'll do that again. That was cool. See, there's the blood flow. Back to the confluence of sinuses. And then from the confluence of sinuses, it's going to go through the 2 transverse sinuses, which are depicted here. They're really on the outside of the cerebellum. And then from the transverse sinuses into the internal jugular, and then back to the heart, the other organ. Some people think the heart's important. But essentially we're going to, again, go from the deep cerebral veins to the superficial cerebral veins into the sinus system. Superior sagittal and straight to the confluence, then transverse sinuses into the internal jugulars. And here's just a posterior view showing the dural sinuses. So this is which? Superior sagittal, and then this region? Confluence, and then these? Transverse, and then the straight would have to be in there. So we really can't get to that. And then just regulating cerebral blood flow, there's a ton of factors that are going to cause changes in cerebral blood flow. Metabolic changes, we know that hypoxia is going to cause the arteries to, obviously you're not going to get as much blood flow, so they're going to cause them to dilate, so to increase blood flow. Carbon dioxide, pH levels affect it. There's tons of other factors. We know metabolic factors. We know neurotransmitters. So glutamate is an excitatory neurotransmitter, so what do you think that does to our blood vessels? Dilates them and causes an increase in CSF. So blood pressure, certainly the number of collaterals they have, whether or not there's an occlusion is going to affect it. Almost any substances that's associated with the metabolism or the neural transmission of the brain is going to affect the blood vessels. So what you actually see on the smooth muscles and even on the endothelial cells of the blood vessels to the brain is you actually see GABA receptors, you actually see glutamate receptors, so you see that on top of just the neurons as well. So serotonin receptors, all of it. Questions? And I thought next time we'll talk about the various types of stroke and how that contrasts to having a head injury. All right. Now you guys have a meeting, right? All right. So you get a little breather.